of our discussion was the following. We concluded that we had a BRST current, this JB, which was equal to C times the matter stress tensor plus BC del C plus 3 by 2 del square C. We checked that this BRST current had the property that its OPE with B and C had a pole. We checked that the BRST current had the property that its OPE with B and C had a pole, and that the pole was precisely precisely matched the transformation of B and C under the BRST charge, which we derived using other means. Okay, and therefore we concluded, okay, that this quantity here was the BRST current, the current that generated the BRST transformation for our system. Okay, now there are two bits of algebra that I wrote down for you that were important, so at least one of which we should try to check. Okay. So for the next 10 or 15 minutes, we will do these algebraic checks. Let's see, what had we checked? We checked the OP of this with B and C. And there are 3-4 things I would like to check. So let's do the following. The next thing I'm going to do is to compute the OP of this BRST current with a matter primary operator, with a matter primary operator of dimension h, a holomorphic matter primary operator of dimension h. Okay, so let this here be a matter primary operator of dimension h, and we're computing JB of Z with O of 0. We want only the singular pieces, so it's totally trivial because these two things do nothing, and the C goes along to the right. Right? So we've got, in the first step, we've got C of Z, and we get, here we get O of 0 by Z square, plus del O of 2 times H by Z. And then at the next step, what we would have to do is to expand this guy, because we want all the singular pieces. So this will be C of 0, HC of 0, O of 0 by Z squared, plus del O of 0 by Z with C of 0. Here we don't need to expand, right, because it's already just 1 by Z. Okay, but in this term we need to expand. So we also get plus del C, H del C O of 0 divided by Z. Okay, so in particular, we conclude that QBRST commutator with this matter primary operator is, as usual, just the pole in the expansion. Okay, so that is equal to C of 0 del O of 0 by 2 by Z, sorry, no by 2, plus H del C O. Okay, and if we put the special case H equals 1, okay, then this becomes del of C times O. This will be very important for us. Why will it be important? It will be important because, well, we'll see why it will be important. This will be important in our string scattering amplitude formula. This will be important to show the BRST invariance of the integrated vertex operators. We'll come to that. Yeah. Okay, so that when you insert a matter 1-1 primary, it's not BRST invariant. Do you remember what our insertions were? Our insertions were C times O. Okay? Or at fixed points, or integral d2z O at arbitrary points. We'd already argued intuitively that O had better be a 1, 1 prime. Okay? Since H is 1, we're coming back to this. We'll come back to this in a moment. But since H is 1, look at this d2z. This thing is not BRST invariant, but its transformation under BRST operator is a total derivative, and we have an integral. So provided the integration domain has no issues, this insertion by itself is BRST invariant. You know, that's very important, because you remember we said that the only things that we're going to allow ourselves to calculate are BRST invariant insertions in this theory. So the whole string scattering amplitude had better be BRST invariant. Okay? So anyway, we keep this in mind. We come back to a thorough discussion at this point, at some point, but this is the reason that this is important. Now this has already motivated the next thing we want to calculate. Okay. The next thing we want to calculate is what's QBRST with CO. Let's do that, and then, yeah. So suppose we take QB, so we want the OP, JB, with C times O, where O is a matter primary. Okay. Now we're going to get, well, let's see what we get. First, we will get contribution from here and a contribution from here. Nothing from here, because C with C has no singularities. Only B with C has a singularity. Okay, so let's do it piece by piece. Let's first take the contribution from here with them. Okay, so the first contribution is C of Z times C of 0. Okay, then we get O of 0, H O of 0 by Z squared plus del O by Z. Now, it looks like there are two terms. We can set C, this is equal to 0.
But that will be anti-commuting.
Exactly, but that gives you C0 square, which is 0. So we have to take the first derivative. Okay? So this term, where we just set things to 0, so path that came from the del O, is just not there. On the other hand, this term is there. Okay? And that gives us del C of 0, C of 0, H times O of 0 divided by Z. Is that clear? Okay. This is term number 1. So we keep it in mind. But we also have the term that we get from BC DC acting on C times O. So what will that be? That will be BC DC. Always conformally normal order, right? I'm not writing that. Just save writing. BC DC, everything's at Z. Everything's at Z. And then C of 0, and then O of 0, which goes around to the right. Now we take the B through, no sign, and we use BCOP. So we get C del C O of 0 by Z. These two were at Z, but since there's only a pole, we can set them to 0. So we get C del CO, and we get del C CO here. So you see that what we get is 1 minus H C del C O of 0 by Z, because this is del CC and this was C del C. Again, when H is equal to 1, this just vanishes. Okay? So when H is equal to 1, this guy here is BRST closed by itself. It's good, you see, because this was a fixed vertex operator. So it would not have been good enough if it was a total derivative. It didn't come with an integral. Okay? So this was some fixed vertex operator, yeah? And so it had better be BRST closed, by itself if our string scattering amplitude formula is going to make sense. Which we're seeing? It is. Okay, let's keep going. The next thing we want to do is well, this calculation we've already done, but I quickly remind you of it because I want to make a point we didn't make last time. The next thing I want to do is to do JBRST times B. We did this last time to check that the transformation property was the right thing. We got T on the right hand side. Let me quickly remind you. JBRST times T, let's quickly remind you. The first term gives C of Z, B of 0. So that first term will give us Tm by Z from here. And then there are two terms from here. Okay, let's work them out again. The two terms from here, let's see. So it's B of Z, and then we contract either the C or the del C with B of 0. So let's see, when we contract the del C, we get C of Z times minus Z square. C of Z times minus Z square. And when we contract the C, we first flip, so we get a minus. So we get minus B of Z del C of Z by Z. Okay. And this was the thing that we, okay. So this was the thing that we claimed was equal to T ghost. So let's see. Let's write this as T ghost was, what was it? B del. Well, first let's expand this out. So this clearly is just del of BC. So it's minus del of BC by Z square minus B del C by Z by Z. So I'm expanding, so I'm just keeping the pole part. I'm ignoring the 1 by Z squared. Okay. And now we get, yeah. So now what there was a minus 2 of del BC, right, in the stress tensor. With this one?
Yeah.
Both.
Both of them are 0.
Everything now is at 0.
Just from the line above it, right? Right, so the last term over there.
Yes?
So it's 0, then the next term, yeah.
I'm sorry, I'll do this more clearly. Here, there is a B0 C0 by Z square, which I'm ignoring, because I only want the 1 by Z. Then there's the derivative of this thing by Z. That's del of BC by Z. And then there's minus B del C. Okay, yeah, there are other things, but they're regular. Okay, and so we'll write this as, this term was Tm plus, I'm going to write it as del BC minus 2 del of BC, the whole by Z. I'm just adding and subtracting a del of BC. And this was the ghost stress tensor. Del BC minus 2 del BC was the ghost stress tensor. So this was, we worked out last time, but I'm just reminding you that JB of Z with B of 0 gave the stress tensor at 0 divided by Z. The full stress tensor, matter plus ghost. Okay? Now, why is this important? Well, this was important firstly last time to check because we wanted to be true that JB on acting on B of Z gave T of Z. That the ghost commutator with B was T. That was part of the BRST transformation rules. But the other thing about this is the following. Suppose I'm interested in computing the anti-commutator of QB with BM. What is BM? As usual, B is expanded according to its weight. B is a dimension 2 field. So B of Z is expanded like Bm by Z to the pi m plus 2. That's the definition of Bm. And I'm interested in computing QB times T times Bm. So Bm is equal to Z times Z to the pi m plus 1 B of Z 1 by 2 pi. Okay, so now this is a commutator of two charges. Now anti-commutator of two charges, both of which are. And according to our general rules, that just is the residue, is the charge whose current is the residue of the OP between this current and JB. Okay, so we need to find the residue of Z to the pi m plus 1 B of JB of Z with Z to the pi m plus 1 of B of Z of
W.
yeah, that's W. And JB of Z, take the residue as Z goes to W. Okay, but you know W is just a number. Okay, we want the residue as Z goes to W. Right, we want the residue as Z goes to W. We could have done it the other way around and then it would be more complicated. But we'll do it this way around. We take the residue as Z goes to W. And we want the residue as Z goes to W. So this quantity here in Z is just plain Z. So we just want to pick up the pole. So we got residue of T of Z, T of W. Yeah, the residue is just T. So the current is the charge whose current is T of W, W to the pi m plus 1, B of W. No, B of W, sorry. It's as you said, B of, there was a B of W here, but not here. Yeah. Exactly. And therefore, this is simply Lm. Because T is also expanded just like B. T is equal to sum over M, Lm by Z to the pi m plus 2. And therefore, if you multiply by m plus 1, you pick out Lm. Okay? And so we've concluded that QBRST with Bm is equal to Lm. Okay? In particular, something that will be very important for us will be that QBRST with B0 is equal to L0. Now, why is this going to be important for us? First, sorry, any questions, comments? Is this clear? I'm sorry. I'm saying that what we get is the charge whose current is this current. So we want to take, the answer is integral res dw by 2 pi I. So the answer is this dw by 2 pi. So the commutator is this, and therefore z. That's what I wanted to say. Is this clear? Any other questions, comments? In the OP of JB and B, there is a double pole term, but we only need the residue of the pole. Now, had JB been dressed by some other function of W, you could have Taylor expanded that other function of W and picked up a single pole. But JB is by itself. You know, we could have done this calculation two ways. We could have taken the residue as Z goes to W, or as W goes to Z. And if we'd taken the residue as W goes to Z, you'd have had to worry about what you were talking about. And it would have looked more painful, and in the end you'd have got the same answer. Okay? So that's why I organized the calculation taking the limit, the residue as Z goes to W, because there's no funny stuff. Okay? The other term would have been some total derivative and would have vanished. Okay? So I'm just doing the calculation in a way that makes it easy. Is this clear? Okay, excellent. Any other questions, comments? Okay. So, what is the importance of this result? The importance of this result is that, well, this result is very important for the following reason. You might remember that when we worked out the BRST quantization of the point particle, we did that quantization of the point particle action in great detail. And we found that if you looked at the BRST cohomology of the point particle, it actually consisted of two copies of physical Hilbert space. But we found that the part that would give us non-trivial answers, the part that we would really identify with the actual physical Hilbert space, and the part to which we are able to physically self-consistently truncate, was the part of the BRST cohomology which is annihilated by B0. Do you remember? There was a Hilbert space built on down, that's the part annihilated by B0, and there was a Hilbert space built on up. And the states in the Hilbert space built on down were closed only when you were on Marshall. P squared B sum squared equals 0. The states on the Hilbert space built on up were exact for every value of P squared plus M squared, except P squared plus M squared is equal to 0. And I gave you a sort of vague argument, and I promised we would do a calculation, which we'll do with this when we do string theory. But I gave you a vague argument that the second term, that these states would always give you non-interesting scattering amplitudes. And the argument was that at least if you're computing some off-shell correlators, these correlators would be 0 if you're anywhere except bang on shell. And then since all correlators are analytic functions, you never have things, non-analyticities like delta functions. That ensured that these correlators would be 0 even on shell. Okay? This statement I will justify cleanly in an actual calculation, in an example, in the string case. But for now, we will just assume that something similar is going to happen. So once again, we are going to look at the part of the Hilbert, the part of BRST cohomology that is annihilated by B0. Okay? So you remember that in our BC system, the 0 modes of B and C generated a two-state system, up and down. And you know, for everything that happens with down, you'll have something happening with up. That doesn't do very much. It's very much like the point particle. The point particle also had the up and down. Okay? And we're just going to focus on the part, like we did in the point particle example, the part that is built on this down vacuum. Which is to say, we're going to focus on the part of the Hilbert space, which is annihilated by states this is equal to 0. Now, as I've said, I will show you an example that this is a consistent. Now, exactly. Now, if this is the case, and we're interested in the BRST cohomology. We're interested in states that are so what we're interested in physical states. We're interested in states such that B0 psi is equal to 0. We're also interested in states such that QB on psi is equal to 0. Okay, so we're interested in states such that they are annihilated by both B0 and the BRST cohomology. I mean BRST charge. Okay, so what we do is to act like this. So QB with B0 on psi has to be equal to 0, because one term in this product is killed by B0 and the other term is killed by QB. But we know that QB times B0, anti-commutator Q, just by algebra, is equal to L0. So we have L0 on psi is equal to 0. So if a state is annihilated by both B0, okay, and the BRST charge, then it is annihilated by L0. That follows from this algebra. So those states that are QBRST closed and are annihilated by B0, we will sometimes call this the physical sector of our theory. You know, the part of state space that's annihilated by B0, we'll refer to as physical sector of the theory. Okay, so the states that are annihilated by both QBRST and lie in this physical sector, that is annihilated by B0. Okay, these states must obey L0 on psi is equal to 0. Now, notice what kind of operators, using the state operator map, we can connect this to an operator. So what kind of operators can we get? One variety of such operators will be operators that are built with C acting on a primary of dimension 1. It doesn't have to be primary for this thing. Any state of dimension 1 at this point. Just a state of dimension 1. Okay? Because C at dimension -1. And the state in question has dimension 1. Okay? So this shows you once again where this dimension 1 is coming from. Okay? If you want something that is C times a matter operator, like the fixed vertex operators in the string scattering amplitude, then once again, for it to be BRST closed, it had better be that that fixed vertex operator had dimension 1. We're going to carefully analyze BRST cohomology. We completely characterize it. So we will show that there is, the final statement will be that there is, in every BRST cohomology class, there exists a state such that it is of the form C times O, where O is dimension 1, 1, and moreover, O is unique up to certain equivalences. We'll come to that. Okay. I will explain this to you in some detail. Okay. Fine. Okay. 2 or 3 last bits of algebra. Okay. There are 2 bits of algebra that are sort of important. I'll do one of them and leave the second one as an exercise. Okay. The one that's really crucial we'll do now. And that's this. I want to find JB of Z with JB of 0. This is probably the most complicated OPE in the process that we'll have to calculate in the bosonic string. But don't worry, we'll calculate more complicated things for the fermionic string, just in case you're getting disappointed.
Yeah, you have given the result in the last class.
I'd stated the result, but since it's such an important thing, I'll go through it.
Yeah.
I'll go through it once. Okay, so we have C times T M of Z, Z plus B C del C plus 3 by 2 del square C. Okay, and once again we've got C T M, but now it's 0 plus B C del C plus 3 by 2 del square C. Okay, that's at Z and that's at 0. Okay, so let's roll up our sleeves and, and do it. Okay, so what we're interested in is all kinds of stuff. But mainly, the thing of interest to us is the pole. But you know, in order to compute the pole, you have to get the higher things right, because then you have to Taylor expand. Okay, so we'll have to get everything, accurate in this way. Okay, so let's take first term. The first term has stuff with the first term and the second term. So let's do first term with first term. So that's C of Z, C of 0, and then we just use the TTOP. Okay, so that's C matter by 2 by Z to the 4 plus T, no, sorry. The C matter minus 26. This is C matter minus 26. No, this is C matter. This is C matter, sorry. C matter by 2, sorry. C matter by 2 by Z to the 4 plus 2 T matter of 0 by Z square plus, okay. Now I don't have to keep the next term, because since this was C of Z, C of 0, we're going to be taking
life
at Z. So this term with this term, this first term with the first term, let me collect terms up here. Okay, let me collect terms up here. Is del C, C, C matter by 2 by Z cube. Okay, but now we have to keep going, because what we're really interested in is the pole. Okay, so what I'm going to do is just keep track of the pole. Okay, I'll leave it as an exercise for you to calculate it. So here what we have to do is to expand this further. So
Del cube C will have to expand.
exactly. Exactly. Now, just a minute. So why don't we just take this whole guy and Taylor expand it?
Exactly.
Okay. So this guy is del MC by Z to the power m del MC by m factorial. What? We want to see that q squares to 0.
Yes. So you will show that this C matter has to be 26, that kind of thing, right?
That's just that. Just that. Just that. Just that. Of course, we could just, anyway, let me just do it. Yeah. Yeah.
Del cube C over C.
Over
Okay.
over C matter by 12, right?
del C C 2 del C C Tm
this term is this,
yes,
right?
and 1 over 12, yes.
Cm by 12 del cube C by C.
Yes, yes, indeed.
Okay. Let's take the next term.
And the other is 2 del C C Tm Tm.
2 del C C Tm.
Yeah.
That's right.
Yeah. And these are the only terms
That survive for the pole.
Yes.
Excellent. So we've got the first. We've got the first guy. Now let's take this guy with this guy.
Yeah. That will have.
That's quite easy.
Yeah, that's CB. That's just 1 over 1 over Z. So
That's right. So this term.
yeah, Tm0.
Yeah.
C0. Tm C del C.
Tm0. C0. Yeah. Tm C del C. Exactly. Tm C del C is this guy with this guy.
Yes.
And this guy with this guy is nothing.
Yeah.
Good. So we've done 1/3 of the work. Okay. What? We should just be a bit careful because the z's are in different places. Which term? You mean this with this? That's what you're saying, right? Let's just work it out. Might be, but let's just work it out. It's also very easy because we just take in this case because there was no z expansion. This was just C del C T. C del C T. So that's 2, as you said. That was this term with this guy. Okay, then there was this term with this guy. It's just amount of a pain. The problem is that C interferes with the T constraint. It's not like C tends to matter. Yeah, I'm just wondering if it's worth it. But okay, let's quickly, let's do it once. Let's do this guy with this guy. Okay, so what do we have? We take the B across here, then we take the B through that, and we take the B with C. Oh God, what a pain it is.
There will be 4 contractions in total.
Well, there are the contractions in which
Yeah, the 2 of them will be identical.
there'll be contractions in which
I know, but you need a 1 over Z squared, so the only one's B and the del C, so you get the 1 over Z squared, so that's how it's going to be here, and the other ones will actually go.
yeah, there'll be a contraction which the C from here, one of the 2 C's from here hits the B here, and one of the 2, the B here hits one of the 2 C's from here. So, the terms in which there are 2 contractions, there are also terms in which there's 1 contraction.
Oh.
And we have to keep them all. Maybe, should I just skip? It's not teaching us anything, right? Okay. It's just too painful. Okay. The whole point, as I told you last class, is that when you go through this whole exercise, you get JBRST of Z. Please do it. Please do it. It's once in your life you should do it. Okay. Maybe not twice. Okay. I had a postdoc friend that in the US who, a Japanese guy, who told me that there was a saying in Japan which went, "The wise man climbs Mount Fuji once, the fool climbs it twice." And I thought it was a very deep thing, and I went later when I went and visited Japan, I went and told my host, I heard you have the saying, so I said, I've never heard it. Then I went back to my postdoc friend and said, my host had never heard this. Where did you hear it from? I've never heard it, he said. Either I dreamt it or it's just the advice not to do the calculation twice. Okay. Anyway, So we've got the BRST charge. The important thing was there was other stuff, but we get C matter minus 26 by Z. Times C del cube C. You already saw the C del cube C coming around. The other things all cancel out. This term doesn't cancel. This came with this. The CM. In fact, you see the CM
So that will
by 12Z. CM by 12 by Z. The CM by 12 you've already seen for me. Okay? The rest you have to work harder to see. Okay? The important point here is that this whole BRST procedure, therefore, QB squared in arbitrary dimensions is equal to Cm minus 26 by 12. And therefore, QB squared is equal to 0 only in 26 dimensions, when C matter is 26. So this, as I mentioned last class, is the BRST's way, BRST charge's way of saying that there is a problem unless C matter is equal to 26.
Stress tensor is ideally 0 is for some reason.
What do you mean?
So the Gauss law.
Yeah, the reason the way the stress tensor comes out to be 0 is as we've seen.
Yeah, so I am saying that because it was a Gauss law, so it better be something Q exact.
Yeah, and we saw where the stress tensor had to be 0, right? Because Q BRST on B was equal to stress tensor. I mean JB and B was equal to TZ,
Yes.
which meant that Q BRST on B was equal to TZ,
Yes.
which meant that T is B acting on QB on something, and therefore it was Q exact. Yes.
stupid question I have to clarify some technicality
Yes.
of this BC del C term alone.
Yes.
Let's say we have just one contraction where one of the B's contracts with one of the C's
Yes.
here. So in the remaining terms, we'll have one B's and three C's.
1B and 3 C's.
And
Where will that cancel with?
yeah, probably they will cancel between themselves in some intricate way.
Let us see that. Why don't, okay, so your question is, can we just compute the pole part with 1B and 3 C's? That part we can do. You see, the only place it can come from
Is again.
um,
B's. I mean, it has to cancel between itself. Right?
is this term, let's see. There's also, of course, this term, which should not play a role. Let's first look at this term with this term. So what we're going to get is this B contracts with this guy, right? These two people, and this B contracts with these two guys.
Yes. This is the fully contracted part.
No, so you were interested where one of them happens.
Yeah,
right?
only one of them.
So let me take the guy where only one happens. So let me take this guy happening with this, and this guy happening with this,
Yeah.
and then the other. Let's just work
Yeah,
that out.
I think, probably because of the anti-chemical.
Probably, let's check that. So this is CZ del C of Z. Now, here we will get B of 0. We get a minus sign, and then we get, let's say when it contracts with this, that's by Z and del C. That's one term.
Yes. Yes.
A second term is when this guy contracts with this.
Yeah.
So then it goes to 1, 2, 3, 4. So you get a plus.
Yeah.
You get a plus
One over
1 by Z, and then it remains plus because the derivatives of this guy. So plus C del C BC by Z squared, and
Yeah, the first two terms are CZ del
at Z.
At Z.
The remaining two are at 0, right?
Yeah.
Right.
Yeah.
And you agree with the sign, right?
No,
Minus 1 by z squared. Why?
derivative.
But this is derivative on the second argument. So that cancels the minus. Right? So that was the first two terms. Let's take the next two terms. The next two terms are when this b hits this guy. Okay, let's get those guys. That's b of z, and then this b hits the del c. So that's c of z del c. Now we get 1 by z. Now this is a minus by z square. C of 0 del c of 0.
Yeah, and that will cancel this. That will cancel the second term above.
That will.
No. Oh, no, it might not. I'm sorry. It will be clear. Yeah.
It will.
It will.
It will cancel the z square part of it.
Yeah. Yeah. At least the z square.
Okay, but maybe not the pole part.
Yeah,
So
yeah.
we'll do that carefully. Okay, and then there is a term where this guy hits this guy.
Yeah.
So that's minus b of z del c of z by z c del c. Right? Yeah, looks good to me. Okay. Do you agree?
Yeah.
Okay. Now we want only the z, the pole part. So these two are just pole by themselves.
Yes. And they are.
And this is b del c c del c. C del c b del c.
Yeah.
They add up, right?
They add up, yes.
B del c, c del c, c del c, b del c. So
Yes.
that's minus 2 c del c b del c by z. And now let's look at the Taylor expansions from here.
Yeah.
Okay. The first term here is we only want the Taylor expansion. So that's plus del of c del c bc.
Yes.
Okay, everything is just a pole, so okay. And this is minus del of bc c del c.
Yeah. So there are two del c is over there.
Ah,
So that cancels.
that's just 0.
Yeah.
That's just 0. You're right. You're right. This is just 0. Right? And how did that happen? Yeah, I just wasn't paying attention. You're right. This was just 0 by itself.
Yeah. Each term individually had to be 0 at the level of poles.
Right. And now let's look at this term.
Yeah, and that will. Yeah.
Why is this 0? But what about the del,
Del
square
for
c?
E for c square. That will
Ah,
be
c square, exactly. And what about this term now? Same way. Either we get a del b, if we get del bc, that's or del c. Excellent. So all the terms are 0. Okay. And of course, this will in the end not contribute anything because this was just put there for fun. You know, it shouldn't affect anything basically. So the important term is this with this. Okay, excellent. Okay. Yep.
The 2b squared, that's one over there. We started initially with showing that our symmetry was infimorphism and wild, right? Then we did a Fabio-Campos procedure, and then we found BRST symmetry. And then we found that the BRST symmetry is having a problem with us. Is this just a wild anomaly showing up again?
Exactly. It was
Is
the
this general? Like if I have a theory with an anomaly and I try building the BRST symmetry from that
Yeah.
anomalous symmetry, I'll end up with something like the BRST is not working.
exactly. It's just that the BRST symmetry is a sophisticated version of gauge symmetry. And if gauge invariance wasn't an invariance, you can't mod out by it. And that's what this is showing up.
So the first time we saw this 26 showing up was all the way in the beginning when it seemed like we were dealing with Lorentz invariance?
Yes.
Is that
Also related? How is it related?
Yes.
Okay, it's related in the following way. You know, I'll answer first with an analogy. Well, forget the analogy, it's just very clear. Okay, see, suppose our theory was non-anomalous. Then we can work in any gauge and get the same answer. So if our theory was non-anomalous, then we could work in light cone gauge and be guaranteed to get an answer that was Lorentz invariant. Why? Because we could instead have worked in this gauge. And in this gauge, answers are obviously, manifestly Lorentz invariant. So if it didn't matter which gauge we worked in, then the Lorentz gauge had to give us answers that had all the symmetries that you could see in any other gauge, in particular in this gauge. Conversely, if you work in Lorentz gauge and find an answer that violates gauge Lorentz invariance, what does it mean? That it isn't gauge invariant, because otherwise you could have worked in this gauge and got answers that were manifestly Lorentz invariant. So this is once again an issue of gauge invariance, because were the theory to be genuinely gauge invariant, you could have worked in any gauge you wanted to, and got. This is a general thing. You know, if you are careless about gauge, the theory you're working with doesn't preserve some invariance you're trying to mod out by, then you fix that false symmetry in a way that violates some global symmetry of your problem. Typically the way it shows up is that global symmetry, which you expect by some miracle in the end to be restored, so it's not there in your calculation, won't be restored. Shows you that the gauge invariance that you were appealing to for that miracle was not true. Right? So it's all the same thing. Okay. And this is the most calculationally useful version of that problem, of that issue, this BRST. Because as you will see, it's what really allows us to make sense of the string scattering problem. Okay? So that's why it's really the most useful way of thinking of it. But they're all, conceptually they're all the same. Okay, great. Fine. Now, what we're going to do is, as a warm-up, what we really want to do is to prove, what I want to do now in the rest of this class. Oh, I'm going to have to go early today, unfortunately. So I don't know if we'll get to this class, but certainly by tomorrow, we want to prove what's called the no-ghost theorem. That is the problem that you were asking me about, of completely characterizing BRST cohomology. Okay, it's a formal exercise, but it's a beautiful formal exercise. It's one opportunity to behave like mathematicians in this. And it's a beautiful exercise, and it's an important exercise. We'll go through that. But before doing that in generality, what I want to do is work it out at level 1 very explicitly. Okay? So let's suppose we've got a Hilbert space. Okay. So we're in the ghost vacuum. Okay? We're in the ghost vacuum. This is not the state corresponding to the identity operator. State corresponding to the C operator. Okay? The state with dimension -1. Okay? And we're in the matter vacuum. So we're in 0, 0. Vacuum and vacuum. Okay? And what I want to do, so if we want to write this in C language, this is the state C and identity. It's the state dual to C in the ghost sector and identity in the matter sector. Okay? And what I want to do, so this is the simplest state in a Hilbert space. So we're looking at the big Hilbert space. Right? The big Hilbert space that we get by quantizing all 26 dimensions of the harmonic of the the matter sector, as well as both B and C in the gross sector. So this is a Hilbert space built out of 28 oscillators. Okay? And the point is to compute the BRST cohomology in this Hilbert space. And we should find the same answers in light cone gauge. You remember light cone gauge, we found states built out of 24 oscillators. Okay? So we should see the same thing. Okay. Now, instead of working in vac here, let's instead work with e to the pi k dot x. Some zero mode momentum in the x directions. Okay? So, the first thing we're going to do is to ask, what do we get when we act with the BRST operator on this state? Okay? So, we want to know what is QB on C times e to the pi k dot x. Hello? Sorry. Huh? Yeah, I'll come very soon. Okay, I'm teaching a class now. I'll end it in about 10-15 minutes and then I'll come. Yeah. Okay, yeah, chat, bye. Okay? So this is the quantity we want to calculate. What is QB C on? Now first some general discussion in this context. First question, what is the weight under L0 of QB? No, of QB.
Oh, QB is it?
Yes. Yeah, so I really want JB. What is the weight under L0 of JB?
2 minus 1.
Hmm?
There is a C times 2, so 2 minus 1.
Yeah, exactly. So JB is C times T or C, so there's 3 here. Yeah, exactly. So JB has weight 1 and therefore QB has weight 0. It's integral JB. QB, which is integral dz of JB, has weight 0. So if you take the commutator, the anti-commutator of QB with an operator, the dimension of the operator is unchanged. Whatever the dimension of the operator you get after taking that operation is unchanged. Or in state language, if you act on a state with QB, it doesn't change the energy of that state. Okay? So, since we're interested in the problem of calculating cohomology, okay? We're interested in the problem of calculating cohomology. We can calculate that cohomology energy level by energy level, L0 by L0. Right? Because QB doesn't mix states between different values of L0.
Yes. Yes.
Moreover, we have already seen that we're only interested in states at L0 equals 0. Because QB, anti-commutator QB with B0 was L0. So we're actually interested in the problem only at L0 equals 0. So this is really what Polchinski calls physical states. There's physical space. That is the subset of Hilbert space, of this full Hilbert space of these 28 oscillators that have L0 equals 0, zero energy, and are built out of and highlighted by B0. That is the part that we call physical Hilbert space. And we want to compute that cohomology. Okay? That the cohomology makes sense on the spaces, on the states that annihilate B0, that are annihilated by B0. This also follows from the fact that QB on B0 is equal to L0. And so for the particular set of states where L0 is 0, QB anti-commutes with B0. And so the if you have a state in the cohomology of QB which is annihilated by B0. That doesn't mix with states that are not annihilated by B0. Okay? So the problem of finding the cohomology within the sector in which L0 is equal to 0 and B0 annihilates states is a well-posed question. Okay? Great. So now we're interested in finding the cohomology in this subsector. We want to focus on states with L0 equals 0 and that are annihilated by B0. No. Well, firstly, the vacuum does not have L0 equals 0. The vacuum has L0 equals -1. Okay? States of this sort can have L0 equals 0 provided alpha prime k squared by 4 is equal to 1. Okay? So this L0 equals 0 will give you the mass shell condition.
All you said that I have a B Hilbert space.
Yes.
I have chosen a particular part of it,
Yes.
and I want to see if there is a BRC cohomology totally within this class.
This class.
And that will make sense provided that your operators, BRST operators, do not take states from this class to
Outside it. But
This is the
this is the condition. It's the fact that you act with a BRST operator on a state that has L0 equals 0. It remains L0 equals 0.
it is closed under the action of.
And you act with it on a state that's annihilated with B0. It continues to have be annihilated by B0 just because B0 moves through it.
And we care what it does on physical states.
And we don't care what it does in non-physical states. This is our problem.
U that is not an immutable operator. Could it be that some state which is outside this part, outside this particular sector,
Yes.
once you act with QB on that state,
Huh?
that gets a contribution, it gets at least a projection on this Hilbert space, because Q is not an immutable operator.
Could it be that, so could it be that states are outside the space are exact? Because the action of QB on states outside the state is a state in this space. That's what you're asking?
Yes.
Maybe. We don't care. Yeah. Yeah. We're just interested in this part.
Okay.
Now, that is well defined by itself. There may be some larger problem, but that's not of physical interest.
Okay.
Okay? Yeah. So, now what we want to do is to look at, so first let me do this. Right. So now you see that nothing in the BRST operator is going to change the momentum. Right? When you act with this, the only part that acts on the matter stress tensor part is Tm. Tm will give you some number times e to the pi k dot x. So the momentum, we can calculate this whole thing momentum sector by momentum sector. Okay? So first let us consider states that are of this form. C times e to the pi k dot x. Okay? Now those were precisely the states that, you remember we checked that under the matter stress tensor, this thing is a primary operator with dimension alpha prime k squared by 4. In order for this whole thing to be L0 equals 0, alpha prime k squared by 4 has to be equal to 1. Okay? So now what we want to do in this sector is to compute the action of JB on C times a particular matter primary with H equals 1. But we've already done that calculation. Okay? And we got 0. Okay? So the first thing we realize is that this state is part of BRST, is at least Q closed.
Q closed.
C times e to the pi k dot x with k squared, alpha prime k squared by 4 equals 1 is Q closed. It will be on this. Now we want to check whether any state of this form can be Q exact. But you see, we've seen that the BRST operator doesn't change momentum. So it has to be some state of the form e to the power I k dot x times something else. This already has dimension 1.
Therefore, it has to be C, minus 1.
Therefore,
Minus 1.
the only candidate state, see, the only state that it could have acted on in order to, so we want to know, suppose this thing was q exact, then there is a state with momentum k and L0 equals 0 such that q on that state is this state. That's what it means to be exact. Every such state has to have this. This already carries dimension 1. The whole thing has to have dimension 0, so the only candidate state is -1. There's a unique, annihilated by B0. There's a unique state for that. Okay, so there's only this state. You remember the only possible states were the up and down vacuum. But one of the two has been killed because it's been annihilated by B0. You see, there were two operators, C and C del C.
You could have written completely operators, but this condition that B0 has to annihilate is
I could have written only 2 operators. Yes. You see, because you think of it in state language. The vacuum of the BC Hilbert space had dimension -1, and there was two states with -1, up and down. In operator language, it was C and C del C.
C del C was what? Okay, so that's okay.
C del C is the one that's killed because it's annihilated by B0. This is simpler to see in state language. There are 2 states, up and down. You have to have a state with energy in this language, and energy -1. I hesitate to use the word energy because when you move to the cylinder, the energy gets renormalized. So it's just the eigenvalue of L0 in under radial quantization. That's why I'm using this operator language. So it's more convenient to think in terms of states. But in your mind, you want to think of states sometimes.
Once you say that that has to be a dimension -1, you can write lot more operators.
Which?
Yeah.
Only 2 operators.
Dimension -1.
Only 2 operators, dimension minus. C and C del C.
So it does not make some B times
B is dimension 2.
C square is in the okay.
C square is 0.
Okay, fine.
Exactly 2 operators of dimension -1. This is the same language in the Hilbert space. There are exactly 2 states of energy -1.
Okay.
I'm going to abuse energy, okay?
Yes.
Energy under radial quantization.
You don't have many choices.
You have 2 choices. and this one is killed because it doesn't obey, it doesn't commute with B0. The state is not annihilated by B0. Yes.
L0 equal to 0 is not the standalone thing. You need another B0 equal annihilated by B0 equal.
Yes, yes. We always L0 equals 0 and B0 on size equals 0.
In the first case, you got L equal to 0 by defining it with 2 axioms equal to 0 and B0 axioms equal to 0.
Yes. So we first put this and then we derive this. Now both these are true. We want states with both conditions. Okay? So the only candidate state,
All of them have to be given.
what exactly? The only candidate state it could have acted on at this level in order to produce something like this is this. But we know that these states are annihilated by QB. So the only state on which it could have acted to produce something exact, when you act with QB on it, you get 0. And therefore these are not exact.
All of them.
They're all physical. Okay? So at level 0, 0, these are the states in cohomology. By level 0, you'll see what I mean. Matter oscillator level. What? Everything will be at L0 equals 0. The number of matter oscillators excited. You'll see what I mean. So far what we've got is saturate the physical state condition all from the momentum. We will now start saturating it not just from momentum but also using the oscillators.
Not from the 0 mode, but from.
Not from the 0 mode but from the other stuff. Okay? And fine. Now we want to go to saturating the L0 equals 0 condition. Okay. We want to go to saturating the L0 equals condition by using one oscillator from x's B's or C's. All right? So I'm going to shift to state language. Okay, it's just much more convenient. Let me just shift to state language. Let me call this guy, I use this notation. So this was 0 and k. The state corresponding to this operator is 0, which is, maybe I'll call it down, and k. Oh yeah, that's what the state was. Now, the other states that I will be interested in are the following states. C minus 1 on down and k. B minus 1 on down and k. And alpha mu minus 1 on down and k. All of them dressed with some, yeah, all of them with an e to the pi k dot x. That's the k. Exactly. So now the energy of this state was minus 1, but the minus 1 here raises the energy by 1. So all of these states by themselves have energy equals 0. Okay? Except that there's also energy from the e to the pi k dot x. And therefore, if we want to be in L0 equals 0 sector, k squared must be equal to 0. This is the sector of massless states. Okay? You see that if we put the net oscillator level, okay. Now this sector of massless states, you can look at the BRST cohomology in this sector by itself. Why? Because, see, suppose we looked at things with, because it does mix case, exactly. Suppose we looked at oscillator number 2. Suppose we took C minus 1 times B minus 1, net oscillator number 2, then alpha prime k squared by 4 would have to be equal to minus 1. But you can't, if alpha prime k squared by 4 is 0 and alpha prime k squared by 4 is minus 1, the k's can't be equal to each other. Since k's don't mix, the oscillator number, when acting on the ghost vacuum, the BRST problem is a well-defined, well-posed problem, oscillator number by oscillator number. Because it's well-posed k by k, and oscillator number determines k squared. Okay? So the whole BRST cohomology problem in this sector is an independent question by itself. So this set of states, we can independently compute the BRST cohomology. Is this clear? Within this set of states. So all we have to do is to compute the action of the QBRST operator on these states. What? Lots of them are? Lots of them will get ruled out. Well, yeah, we'll see exactly how it works. Yeah, 4 of them will get ruled out. Because 28 has to become 24. Okay. Okay. So let's see. So now, what is the easiest way of doing this calculation? Fine. Let me first do this guy. Let's first do alpha minus 1 mu. Okay. So this guy was the operator del x e to the pi k dot x. That's alpha minus 1 mu times e to the pi k dot x times c. That's what the state was. Is this clear? Okay. Now we'll just compute JBRST on this. Okay, so we compute JBZ on this. Now let's do the calculation. JBZ is what? It's CT plus, somebody, do you remember? What? BC del C. BC del C. Yeah, plus
Yeah, then the other square C term
will not contribute. So let's look at the T times del x del x. Okay. So now we had C times, now T was minus, do I remember right? Minus 1 by alpha prime del x del x. And the OP was x of z, x of 0 was equal to minus alpha prime log of z square. Was by 2? By 2. Okay. So now let's do this. So let's do it fast. So we've got this quantity times plus BC del C acting on C del x. Now we'll be a bit careful. We put an x mu here and an e to the power I k dot x. Okay. One term is from here, here and here. That's very easy. The B goes through. It produces a 1 by z. And so we get C del C C del C del x mu pi k dot x. Bit odd.
This has a 1 by z and then when you expand it to be done.
What? Say again?
If this has a 1 by z, right?
Yeah.
And then when you expand it to the left.
Why don't we tailor expand? Just keep these terms. So as you said, this was this divided by z. Now we just set this to 0. So I'm just keeping the pole. Okay. And then there is, it's a bit odd. Okay, anyway, let me finish the calculation and then we look at it. So then there is a term where you take this guy with this guy. So we keep the, we've got a C and a C. So we only want the double pole. Okay. So we got plus C of z, C of 0, and then we want the double pole. So now we have to do what?
This is basically, write that as like u or some other index, and then you always get something like u. So you always pick up the log. 2 times the derivative of this, it'll be 2 and that'll cancel the half, and then the alpha, minus alpha times cancel the alpha prime, and you just left with del x del x. So this class alpha prime times 1 by this.
Let's see. One of the terms is when this guy hits this guy. That gives a 1 by z square. And one of the terms is when two of these hit this guy. But what about when one of them hits this guy and one of them hits this guy? That is also there, right? Yeah, yeah, yeah. I'm just wondering whether we should probably just do the whole thing operator. Anyway, I'll do this one calculation, then for all the rest we'll switch to mode. I'll mode expand, it'll be faster. But let me just do this one calculation. Okay, so let's do this calculation. So when we get del x, okay, I'm sorry. You know what? Okay, let me finish this one calculation because I'm satisfied not to finish a calculation once you started. But I'll just mode it. What I'll do, which is much more efficient, is the following. What I'll do is to take Q, is take JB dz. And then I will write T of z is equal to, sum over n Lm by z to the power m plus 2. I'll write C of z is equal to sum over m Cm by z to the power m minus 1. And B of z is equal to sum over m Bm by z to the power m plus 2. Plug that into this expression, the expression for j, and then get the answer for q in terms of these c's. This will be a much more efficient way of doing the calculation, because once we have an oscillator representation for these q's, we'll be able to just act on these oscillators using their commutation relations. It'll be much faster. But we'll do that next class. For now, let me quickly finish this calculation since we started it. I'm sorry, I should have done that from the beginning. That would have saved time. But let me quickly finish this calculation. Let me just do this just to see that we can. Okay. What did we get? We got C of, what did we have here? We got yeah, that came from here. That was this term.
No, I said del x and
Ah.
also one of the del x terms.
Yeah, now there's a z cube here as well, right? There is a term which is like z cube, so it's a painful calculation, but let's do it. When I contract this with this and this with this, I'll get a z cube coefficient. Okay, let me do it.
Yeah.
C of z minus 1 by alpha prime. C of z. Now let's contract this with this. That gives x with x. So that gives minus alpha prime by 2. And then we will get two z derivatives,
Yeah.
but with so I get 1 by z square with a plus, because the two derivatives act on different pieces, different x's. We had an option of which two ways of this guy hits this or this guy hits this.
Yeah.
So that's a factor of 2. Okay. Then we get whatever we get when you contract this with this. But when you contract that with that, that's just contracting with I k x power m by m factorial. There's there's m ways.
I k.
Yeah. So you will just get an I k mu,
Yeah.
because this only clicks when this is an x mu, so this will also have to be an x mu. So I k mu times e to the power k dot x. Okay, so I'm claiming that this term here will be I k mu e to the power k dot x, and this came with an extra z, so this is z cube. This is the most singular term. Alpha primes cancelled. Ah,
The second.
thank you. And we have a minus alpha prime by 2. Okay. This is one term.
This, I'm confused with 2, sir, because the logs take care of.
But that's mod z squared. It's
a
z
mod
z
squared.
bar.
Right. Z bar. So.
Yeah.
Yeah.
Okay. Then there was a term where
Only one of them contracts.
where this guy there's a term where this guy these both contract with this,
Yeah.
or these both contract with this. That just gives you the weight of this operator. Since this operator has weight, what?
Because this is the stress tensor.
Because this is the stress tensor, exactly. So that part, the part where these guys both contract with this, or these guys both contract with this, okay, that part will just give you C of z, then C of 0, del x mu of 0, e to the power I k x of 0 by z square, but with weight what? weight 1, exactly. So we'll get it with weight 1 and plus the derivative of both these terms, del of del x mu e to the power I kx c of 0 c of z with weight z. This part we don't need to care about because the c of z, c of 0 will kill it. Okay. This part, of course, we had a c of 0 somewhere which I've lost. I'm sorry. We'll simplify these in a minute. And then what remains is the c with the b that we had.
Yeah.
That was the first term.
Yes.
So we're done, right? Oh no, what about the terms with only one? The terms with only one don't contribute. The terms with only one contraction don't contribute because those, yeah, the terms in which I take one of these and contract with, let's say, this, will give us a 1 by z, but there's a c of z, c of 0. So that will not contribute. So this is all the terms that will contribute. Okay, now let's simplify this. This guy was z cube. Okay, so we will have to take two derivatives of this. Nothing else was at, yeah, both these were contracted away. So we will get this cancels this. We have two derivatives by 2. So this cancelled this. We have two derivatives, so we get minus alpha prime del squared cc into ik mu e to the power ik dot x, and have I got my 2's right?
No, I think this will be 1 over 4.
Let me see.
Because one of comes from the Taylor expansion of C and
No, but there was a
another
2 and a half. That 2 got cancelled with this.
So that 2 got cancelled with the alpha prime.
And there's a Taylor expansion.
Yeah.
Yeah, you're probably right. You're probably right. 1 over 4. Where was this 2 from?
From that
There, there were 2 ways. Yeah, and this half. Okay, sounds good. Oh, no, but what were the 2 in the form? Yeah, there was no 2 in the formula. Right. Excellent. So this came with a 4. 4 plus this term where we just expand to first order. Del cc del x mu e to the power k dot x, and there was this term didn't contribute, and there was this term c del c. Now this and that cancel, right?
Yes.
Okay, perfect. So this and this cancel each other. So what we're left with is this state. Okay, I'm going to go very soon today, I'm sorry. But let me very briefly, oh, I'm sorry. I want to know what this state was. You see, this was the state that we got by acting with the BRST charge on alpha minus 1 mu on down k. But we said that the only things that you will get are one of these states, right? So which one of these states is it? Well, let's see. What we've got clearly is what we get by Okay, so let's, as a quick exercise, let's do the following. In the ghost sector,
What is the other method? There are this C delta kind of
but you're not going to get the C del C kind of vacuum because B0 doesn't annihilate it. Okay, let's just do this. We want to know what is B minus 1 on the state C. So what was B minus 1? B was expanded as sum over Bm by Z by m plus 2. So Bm was equal to Z to the power m plus 1, B of Z. I'm not writing the 1 over 2 pi i's. Okay, so B minus 1, okay, was what? Was equal to just B of Z dz. So if we want to know what is B minus 1 on C, the state C, we want the OP between B and C. Okay? So that was the state corresponding to the identity. Okay. Now, state corresponding to identity operator, okay, good. So identity operator is one of the operators in the game. And what about the state that we get when we act with C minus 1 on C? Okay. So let's see. So what was the state when we act with C minus 1 on C?
Nothing.
Wow.
Because CCL OP, they're from CCL.
Well, let's see. Del C. I think we'll get the del square C. Let's see how it goes.
Oh.
Okay. C minus 1. So C of Z is equal to sum over m Cm by Z to the power m minus 1. So Z square times C of Z. Let's check. We multiply by Z square. We will pick up the term with Z cube. That's C2. No. Sorry. So if we want to pick up,
M equals 0.
we want to multiply by Z to the power m plus m minus 2. Cm is Z to the power m minus 2, and C minus 1 is therefore 1 by Z cube. Yeah, 1 by Z cube C of Z dz. Okay, so what we want is the OP between C of Z, C of 0 by Z cube del square C. Okay, so this quantity here was C minus 1 on the vacuum. Okay, so this, what we just derived here, is that when we act with QBRST on alpha minus 1 mu on down, okay, what we get with some numbers that are written here, minus alpha prime by 4, and so on, the numbers will not be important. This with some proportionality, we get C minus 1 acting on down, okay. That's okay, and that will be important. Thank you. Okay. So we want to do similar calculations for everything. Okay. We want to do similar calculations for every state. We want to calculate QB acting on C minus 1 on down K. Actually, this one's quite easy. Which equation? You're right. You're right. You'll just get 0. You're right. You'll just get 0. So this will be equal to 0. Absolutely right.
It's exact. We're saying this is exact.
We're saying this state is exact. And we also want QB acting on B minus 1 on down K. Okay? This takes some calculation. I'm sorry, I'm going to have to go home now. I'll leave this as an exercise to you. We'll do it again next class. Okay? You know, if you do this, one way of doing it is to, well, just do it, right? So, yeah, okay, just do it, or we'll do it in class tomorrow. Okay? Once we have, see, so what have we got? So far, what we've got is QB acting on alpha minus 1 mu K, I'm not writing the downs all the time, is equal to C minus 1, K mu times C minus 1 K. Okay, we've got QB on C minus 1 K is equal to 0, and QB on B minus 1 K is equal to something. We have to work this out.
C minus 1k got thrown away because it was Q exact.
Exactly. Exactly. C minus 1K has got thrown away because it's Q exact. And
The first state is not physical, but it's not closed.
what?
I mean, the first state is not closed.
The first thing is not closed.
Unless,
Unless something
yeah,
happens.
this is massless state, and then we can choose.
And then Grover's K squared is equal to 0.
No, but we can polarize this in some way. I mean,
Exactly.
SOD minus 2 we can choose.
You see, what we want to do is to take this with an epsilon mu.
Yeah.
And if epsilon dot K is 0, then it is closed.
Yes.
Okay? This will be the transversality condition of photons.
So this will be SOD minus the little group of
It's just the fact that photons are polarized. The polarization of photons is transverse to the plane of momentum, or same for gravitons. And we have to work this out before we start drawing conclusions. Let's do this tomorrow.